Okay, let's kind of get started. Marcus said he just emailed me a link to my math account.
Yeah, your math.
Okay, so oh, you go. Okay. So he's going to he's one of our PhD students in stats, not stats, here.
Right. Yeah. So when you do lasso reach, so you have a response or a variable that you want to predict, and you have lots of other variables that you want to explain, so carry information about your response that you want to predict. And some of them might be very useful, and some might just contain noise, and some might be very similar to others. So when you do this lasso and ridge, your variables are sort of competing against each other. Who should stay in the model and who should not, and what's the size of their effects. And then you have this parameter lambda that's sort of controlling the size of your penalty on the size of your coefficients. And so I had this nice picture. Let's see. So when you're doing ridge regression, where you're having this squared penalty, yeah, exactly. So then, as your parameter lambda increases, it becomes harder and harder for your coefficients in your regression model to be large. So what they tend to do is the size of them tends to shrink. And when you do this ridge regression, it sort of shrinks like you're landing a plane. It shrinks slowly towards zero. Some might reach zero. Some will just be very small. But when you're doing lasso, you're sort of crash landing. So some are sort of quite rapidly crash landing at zero, and then they just vanish. So the effect of this variable is zero, while others stay, and then it's always this case: which lambda should you choose? And you do cross-validation and stuff to find the optimal lambda. Maybe in this case it was somewhere here. So that's sort of what you would expect the behavior of these two methods to show. So intuitively, that's a nice picture in mind.
Yeah, and when lambda is 0, we're back to ordinary least squares.
Exactly.
Thanks, Marcus. That's a good one. Okay, so, oh boy. Dylan's working. Let's see, what time is it in New Zealand? 10:36 p.m. Anyway. Where are we? Here? Right. Yeah, so now we're going to make some simple queries with these graphs. So I can just ask for the vertices, just get the vertices, IDs and attributes like name and age. And this is exactly the same graph we loaded using this examples thingy, right? The preloaded example is the same thing. We can do g.edges and get our relationships. So the edge attributes or source and destinations. And we can do these things, right? We can do g.inDegrees. This is kind of something a lot of people that study complex systems, including David Sumter, remember he introduced us to this culminating workshop on mathematical activism stuff. And a lot of physics people who study networks, they study these in-degree and out-degree distributions and talk about some kind of a power law decay of these degree distributions and stuff. So this is clear. C has 2 in degree 2, the others have only 1. Again, we can do g.outDegrees. So these will work in a nicely scalable way for incredibly large graphs. Of course, you have to throw more worker nodes at it if it's too large. And then you can just get degrees, right? So this is both the in and out degrees. right? So you can run queries directly on the vertices data frame. So imagine in Marina and John's problem, like we'll do this with OpenStreetMaps. When you suck in OpenStreetMaps in this XML format or this Google protocol buffer format, you will have like an ID, which will be the point that's defining, say, a wave, which is a sequence of points, you know, a polyline. So now each of those, some of those points will have lots of attributes like, you know, this is, I don't know, Tiananmen Square and blah, 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 you know, this is some cafe and so on and so forth, or it'll describe the name in multiple languages. XML does that, so it'll have so many different Unicode characters in different languages describing things. All those will be easily representable in this framework. So now you can say, take my vertices, group by, we'll just group by the vertices, and then I want to know, so once I've grouped by, there's all these age attribute, right? So I want to now find the minimum age. So that gives me my minimum age is 29 of that little network. So I'm calling the youngest. You can also run queries on the edges data frame, right? So I can say, take my edges in G and filter it by the relationship equaling follow, okay? And then I'm simply counting. So this will be the number of followers on the graph, 4 followers. Now things get kind of more beautiful. In fact, there were talks in the probability and stats seminars on various latest improvements on things like this. So this problem generically is called Motif Finding, right? And in fact, some of the trajectory problems, some of the problems John talked about, like finding, you know, housewives that have a certain pattern of trajectory dynamics, okay? Whatever, weekdays they go somewhere, get some food, drop the baby. So you basically can define a motif based on some subgraph pattern, and then just search a very large set of trajectories that satisfy this motif, this pattern, right? So we'll play with very simple motifs first. So this one is finding the, find all such motifs. So that means, you know, node A goes to another node B over edge G1. That's kind of the syntax. And B goes via edge G2 back to A. So it's like bidirectional motifs, right? So if we say that's my motifs, find it, it does some distributed scalable computing down under the hood, and then gives you back all the motifs that satisfy this condition, right? So IDB, name Bob, age 36 is A, and edge 1 is B to C. The relationship is follow, and B is this guy, Charlie, and edge 2 is Charlie goes back to B in the relationship follow. So Bob and Charlie follow each other. That's what you can find from this simple motif hunt. And then, yeah, so, and then this is kind of the other way around. Charlie and Bob also follow each other. Okay, since the result is a data frame, more complex queries can be built on top of the motif, right? So we can now mix our data frame with it. So I'm going to have my vol filtered, and I'm going to take my motifs that I just had upstairs here, and I'm going to filter it by the second element being of age greater than 30. So let's find, this is basically finding all the reciprocal relationships in which one person is older than 30. So now you're getting into the sort of proto world of what to recommend to young people. I mean, basically, right? This is So if you have some graph frame representation of some potential clients or whatever, this is basically very, very quick way of going after some population of interest. So motif 3 is search for all directed triangles or triplets of vertices, A, B, C, with edges A, B, B, C, and CA, right? So this is basically triangle hunting. Oh, I guess I solved this problem. Yeah. Yeah, so you basically have Esther to David to Alice, and yeah, and so you should find the other triangle: David, Alice, Esther, and Alice, Esther, David. Okay. Yeah, and you can do further projections for, what is it called? Homomorphism. If you want to forget about the graph homomorphism. I mean, you know, this is all like completely ordered triples. So if I'm because this could be redundant information. If you're only interested in the unordered triangles, then you can just do that again. Okay, this gets more elegant now. So now we can do stateful queries, right? So what is this? So many motif queries are stateless, like what we did. It's very simple to express. Now we're going to get into more complex queries that carry state information along the path in the motif. Okay. So these queries can be expressed by combining graph frame motif finding with filters on the result, where the filters use sequence operations to construct a series of data frame columns. So we're basically rolling out new, growing data frames on the motifs. So for example, suppose one wishes to identify a chain of 4 vertices with some property defined by a sequence of functions. So among chains of 4 vertices A, B, C, D, let's say we want to identify the subset of chains matching this complex filter. Initialize the state on path, update state based on vertex A, update state based on whatever the next vertex B is, and then whatever the next C and the next D. So the final state matches some condition, then the chain is accepted by the filter. Oh gosh, this could be like so many problems, right? For example, think about something Marina told me, some random walk we're doing. You say you have some information on a bunch of travelers, and you know when they're leaving some train station at different times. So you have, like, say, the delay time as another variable. And so, or it could be trains. It could be just trains going from station to station with delay time. So you want to know what is the sequence of 4 consecutive trains that delay by more than a certain time, for example. So you can find motif patterns like this. And this can, of course, be used in some kind of operations research on, anticipating, future effects on whatever commuters. And and it's enough to understand the syntax on this one. So basically, we're going to demonstrate this. We'll first identify a chain of 4 vertices such that at least 2 of the 3 edges are friends. Okay. So the state is going to be the current count of friend edges. So we're just going to keep the total number of friend edges we visit in this chain of 4. Right? So here it is. I first define my chain 4 to be g.find, my motif pattern. And then I'm going to query on a sequence with state C and T. So here's my little function definition, some friends. What some friends do, it takes an argument called C and T, which is a data frame column, type data frame column, and something called relationship, which is also another data frame column. And then it returns a column back. Okay. So then what it's going to do is, when the relationship is friend, then I increment C and T by 1. Otherwise, leave C and T alone. It's that simple. So now we have to apply this function. So how do we do this? So the sequence operation to apply method to sequence of elements in Motif is the following. So first we say while condition is sequence of AB, BC, and CD. These are my edges, the 3 edges between the 4 nodes. And then I do this dot and call the fold left method. The fold left method, remember, is just a method on the Scala sequence class. So fold left is a specific kind of fold, right? It's reduced as fold left or fold right, basically. So what I'm going to do is I have the literal 0, so I initialize my count to be a column of zeros. And then, you know, this is a bit, so this is what I'm starting with. And then what I'm going to do to fold left is I have to specify, you know, this ordered pair, the count, and the edge goes in, right? So this is my sort of map, right? So this count.edge is the input, and then out comes this output from the friend function, the sum friends function. So that'll take the count CNT and the edge E, and then simply apply the CNT and the column of E with the column ID relationship, I mean column name relationship. So I will take my sequence and do this fold left operation as I to accrue the count on the number of friends I see. And then finally I apply the filter to the data frame. So I take my motif chain 4, and then I just say where the condition is this one we just defined is greater than or equal to 2. So that's it. I just get all my paths with length 4 with at least 2 friends. And you know, if we have a column called delay and the node IDs are, say, trains, and Marina, you said there is some API, public API you can use to download the actual train IDs and times. Yeah. So then it's kind of that's a great homework problem. Or, you know, you can definitely blog about this, publish it, and let people just, you know, whatever. Okay. I don't know. This is all a year old, so I don't know what this. Bold idea. Can you think of a way to use stateful queries in social media networks to find perpetrators of hate speech online, or possibly worthy of an investigation by domain experts, say in the intelligence or security domain, for potential prosecution on charges of having incited another person to cause physical violence? This is a real problem. This was I was writing a grant at this time to the EU. I didn't get the grant. But it was a really beautiful problem, and in fact, I was going to talk about it, but I didn't. So here, the main problem was, you know, the only thing it's kind of worth slightly diving into. See, because at the end of the day, you know, you want to do some maths or whatever, but it's nice to get some money for it, right? Especially if you want to have resources. And also, what better way than to like do the maths for some law, right? So this is kind of what we were trying to do. So here, well, you see all of you are now officially, you know, whatever. So yeah, what we did is this. So the main laws, this is what I was going to talk about. So the European Commission and the IT companies announced this code of conduct on illegal hate speech on 31 May 2016. So this is like, you know, Facebook and Google, blah, blah, blah. They all got together with the EU and they signed this memorandum of understanding, or some, you know, like a code of conduct. So the Commission, together with Facebook, Twitter, YouTube, and Microsoft, IT companies today unveil a code of conduct that includes a series of commitments to combat the spread of illegal hate speech online in Europe. This happened before the French election, right? So there was active, like I had colleagues in École Polytechnique who were, I don't know, doing some operations. And so, you know, they really were way more vigilant about fake news, for example, in the French election than they were in the US. I don't know if you. So, but of course, this call is like, this is the memorandum of understanding they signed, but then that particular memorandum of understanding builds on this particular, fundamental rights for European citizens. I'm not a lawyer, right? But I just talked to my brother-in-law, who's a lawyer in London, and I asked him, what do lawyers do? He said, oh, they just keep reading and argue. I said, okay, what should I read? You should read the law. So, I just read basically every law I could chase for this grant, which basically boils down to that, and the actual pieces of legislation I was going to share are a law from '98, and then another one that was revised a bit more recently for the modern communications. And it's a very simple law. It's actually done, it trickles down all the way from the founding of EU post World War II. So they kind of don't want people of certain ethnicities going into ovens again, or minimize this probability, right? So it's really against xenophobia and hate speech and so on. And so how do you hold or monitor that these IT companies are actually abiding by the code of conduct? And that was the main grant. Right? And of course, this is like the real, beyond EU, right? So, this is UN, so if you say something that actually, is an incitement to genocide, it's a real problem. I can sort of, you will be at least held accountable in the International Criminal Court in Hague and so on. So that's kind of the backdrop for that bold idea, right? So that was just a little distraction. So of course, if you can do something like this, this is a great product, right? You can sell this to anyone, right? Interpol or whatever you want. Or, so here's the subgraph. So now let's look at subgraphs are built by filtering a subset of edges and vertices. That's the definition of a subgraph. You just drop some edges and vertices. So the following subgraph only contains people who are friends and who are more than 30 years old, right? So this is the old people network. Old people. Yeah. That's what my daughters would say. Oh my God, yuck, 30. So anyway, Gabby is 60 apparently. So then you can look at the edges. So this is kind of why I was boldly collecting Trump anyway for the last 3 months. Oh wow, by the way, let's look at what's happening in our little collector, right? So I was telling you, we have this, yeah, so let me quickly check this out. So this is still running. So, I boldly threw Trump in because I knew I could do a subgraph operation later and see if he's really, So now this job was running. I don't know. You see, Sweden is very quiet. It's like 3 records per second. You saw it was 25, right? With Trump, one guy thrown in. He's very famous. Anyway, okay, so then we're just sort of visualizing this using our D3 thingy. It's the over 30s friendship network. Now here's a more complex triplet filter. How to select a subgraph based upon triplet filters, which operate on an edge and its source and destination vertices, right? So you view the edge as, in this sort of triplet view. So let's select subgraph based on edges E of type follow, pointing from a younger user A to an older user B, right? This is so I don't know, some impressionable young person is looking or following some older person. So my paths is going to be G dot find, and I want this basic AEB thing. And then I want to filter by the relationship to be follow, and the filter with the A dot H less than B dot H. So again, just pure Spark SQL, data frames, graphs, all sort of coming together. And then Yeah, and then I simply want to define my E2 to be paths.select, e.source, e.destination, and e.relationship. Okay, so finally I'm going to construct this subgraph using the vertices of G and only these edges. So this should just give me what I'm after, and actually, let's see, let's quickly visualize this guy. Okay. Is this what I want? Is it G2 now? What did I do? Yes. So it's G2. Yeah, that's the point, right? So you've got floating, these are unconnected components, right? So, and remember when Simon talked about social network analysis, first thing he was doing was getting the number of connected components. And I do the same thing. You really want to do this. Why? Because once again, if you really want to know the islands that don't talk to each other first. And so for example, even when you have this simple Markov chain in the back of your head, right, there's a lot of the graph algorithms kind of seen in that way. So if you have you know, frog jumping between various lily pads here or whatever, and then there's say this is huge. In this world, this is called a giant component. This is really big, and then there's lots of tiny ones like this, you know, floating around. In Simon's SMA, he had one huge giant component, lots of little ones like this floating around, right? So remember, if you start from here, unless you're a random surfer, right, in Google's PageRank, you cannot go there. You just be stuck here. So, so you want to understand these kinds of topological structures. They're also called topological Markov chains. Yeah, so and then, you know, the notion of stationary distribution gets more delicate when you have these kinds of what is called lack of irreducibility, which basically says you can go from any state to any state. And as I said yesterday, Sergey and Larry's big achievement was that they kind of turned this big worldwide web of lots of disconnected components into one irreducible Markov chain by making this random jump with probability 0.15. Okay, so how's everyone doing? Good. Okay. So now we're going to go into more elegant things. So we just kind of played with basic constructions and queries. So now let's look at standard graph algorithms, right? This is pretty much my pick of the top ones you're going to need for social network analysis for sure, and lots of other basic stuff. So the first one is called breadth first search. So we'll kind of briefly remind ourselves of what that means. And then the second one is this, connected components, finding the number of connected components. And then there's a more subtle notion of strongly connected components, which is something you need for directed networks when you only have directed edges going from one way. It's more subtle actually. And then there's label propagation algorithm, which is called LPA. I hope I do that here. So label propagation algorithms are very beautiful class algorithms, and they are maybe some of the simplest algorithms for what's called community detection. And this is another big buzzword in social network analysis. So you want to, and complex systems, guys who study networks, they call it this, yeah, it's a whole community called network science. You know, there's textbooks on it, big communities, huge meetings. So, there's a lot of people that study community detection, and it's very important. Then we'll do PageRank. Remember, this is sort of our main motivation for Google anyway, to do the pre-bill API. And then we'll also get into shortest paths. And you know, when I was talking in my sort of Twitter talk about getting these population Twitter ideological trees, right, from this weighted retweet networks, you know, remember I had these influential nodes of interest, and then I asked for every user, what is the shortest path to go from each one, you know, from a given influential node to me, right? From another influential node to me, and so on. That shortest path algorithm is actually this one. It's the simpler version of it is this one. So that's called distributed Dijkstra single source shortest path algorithm. That's also a Pregel program. So that's exactly the same structure as PageRank program, and the triangle count is also a Pregel program. Okay. Yeah, I think it'll be great if we go through, finish this before lunch. And then, okay, GraphFrame, user guide on breadth first search. Let's open this in case we get into some troubles. So this is kind of what I read a while back. Yeah. And then you can descend into the API docs if you need. So, yeah, this is basically how I learned stuff, right? So anyone can do this. So what is breadth first search? You have the idea is that, you know, you have some node and some large graph, and then you are expanding outward. So you go to all the out neighbors, all the nodes that are out neighbors of you, and then you sequentially march through each of your out neighbors and go to all of their out neighbors and so on. So if we do it once, that's basically a breadth first expansion with say 1 degree. If you do it twice, it's 2 degrees. And some guys from Google's R&D engineering team in Banff a couple years ago said that Facebook's team said that when Facebook does it 2 times, it's basically end of their disk space. I mean, it's just on the whole world, Facebook. So yeah, 2 degrees out is a lot in Facebook apparently. Yeah, so here is so what is the basic idea? I mean, this actually outlines the algorithm itself. Yeah, so you can sort of write, you know, you can keep track of these things like order in which the nodes are visited during this breadth first expansion. So here you go from 1, I don't know, some canonical order. This is the second guy, you visit third guy, fourth guy, and then I guess you start from this guy 2, so I guess the lowest, and visit 5 and 6, and then this guy has no one. Then you go here 7 and 8, and so on. So it's okay. Yeah, so yeah, and you know, it's not a very complex algorithm. You just keep track of flags, and then if you visit it already, you say I visited, blah blah blah. It's just the same thing. So we don't need to dive too deep into this. Oh, actually, this is cute. Is that an animation? Yeah. There you go. Okay. So let's search from Esther. She's the one that was 60 years old, right? No. Oh, that was Gabby. Yeah, I don't know. Esther's. How old is Esther? 32? Okay. Search from Esther for users of age less than 32. So we basically do BFS, that first search, and then you can do this from expression and give, so here I'm just saying the name is Esther. I want the name to be Esther, and then the to expression, I want the age to be less than 32. So it's basically a filtered breadth first expansion. And this is the initial condition. And voila, so we get, David. Yeah, that's it. It's a small world. So, and then we can also do this. We can either start from Esther or Bob. So it's an inclusive OR, and then do the same thing. So now Esther was went to David, and Bob goes to Charlie. Okay. So we can, of course, limit by edge filters and maximal path lengths as well. So we can say we don't want the path length to be beyond 3, because if you did this, if you did it like this on, like, say, a huge network, it will crash. Like I said, even Facebook supposedly puts max path length 2 on when their from expression is everybody. So yeah, but this is a small thing. So this will be safe for larger ones, and that's straightforward. Okay. So generally, these are sort of nice strategies to explore. So once again, like shooting off the top of my head, in John and Marina's problem, these are very powerful operators. Suppose you ingest OpenStreetMap as a GraphX, which is kind of the one of the notebooks that is cooking. So yeah, and if we can do that, then the main idea would be we can say, starting from this cafe, go, so many, so many degrees, because later on, the way we ingest OpenStreetMap, we ingest it at multiple specifiable discrete resolution. You can say, I want my OpenStreetMap turned into a GraphX or DataFrame object, such that I'm interested in, of course, every intersection, every road segment, but then if the road segment is, say, longer than 500 meters, I can break it into units of 100 meters or 50 meters, however I like, depending on, So when we're doing this stuff for predictive policing, whatever the stuff, depending on the, it's a tunable parameter, depending on the particular, jurisdiction the software would go to, it depends on the speed of the cop patrol car. In LA, it's different, whether they're in residential areas. So if they're going at, say, 15 miles per hour or 20 miles per hour, then you can just break it down, break the road segment so that they have some kind of response time, right? Because there the big sales pitch was, the burglars don't like to burgle if they see cops or something. So that's specifiable, but to go to breadth first expansions, you can start doing very simple things. You can just go out to very specific subgraphs of this OpenStreetMap that satisfy various constraints. Like, I want to find all the bars, whatever you want. So those are all just SQL expressions once OpenStreetMap is ingested into a DataFrame thing. Yeah.
Sorry, that's what
Yeah.
So there's something I'm not understanding, because I thought this last cell actually took like the previous question but added more restrictions.
Yeah.
But what we get is not a subset of what we got before, right? Or is it something else?
So let's see. No, so here I'm only starting from Esther, right? I thought earlier we started from both Bob and Esther.
Yeah, that I get. So
okay.
You get one row there for Bob, but if you get the Esther row, Esther is connected to David.
Yeah. And I wanted the relationship to be friend, right?
Nothing but friend.
Oh, sorry, not a friend. Yeah. Okay, so let's look at this cell. So this is what you want to compare with.
Yeah, I was just thinking maybe you get one answer. So you get Esther is a friend with David.
Yeah.
And then, but shouldn't this list also contain all the ones that are also not friends? So you should also be getting the Esther and Connie and Charlie's connection. There's something about
yeah, I mean, so here we're starting from Esther, and then we want to reach any node whose age is less than 32. And
so there's only one.
Yeah, there's only one, right? So what do we do? Is this the one? Yeah, so here we are starting from Esther, and we want to reach any node that's age is less than 32. That's the same. But now I have this edge filter, right?
Yeah.
The relationship is not friend. So let's comment this out. And okay, let's be. So this shouldn't this be the same as the previous one? You're happy? This is the same as before. So let's sort of see what happens if I have a max. That shouldn't change anything, I think, because it's the default max path length is infinity, I think. Whatever. It's okay. The only difference is this one now. So I'm also saying now the relationship is not a friend, because this will disappear now because they have a friend relationship, right? Esther and David. So now,
which should have been there in the first one as well.
No. So this is basically what we have. The previous cell is the same as this, right? So, but look at the relationship between Esther and Bob. They're friends.
Yeah, I know. So you filter out that.
Yeah.
You
So
get nothing, I presume.
no.
So
No, because
you get a
because I'm now going down the follow paths, whose age may not, the intermediate age may not be 32.
okay, so okay.
Because I got like only the terminal age has to be 32.
Okay.
I think so. I mean, I'm just Does it make sense? Yeah. Well, it's a good question. I mean, please ask these questions because okay, so now let's get into connected components. Yeah, so I think this is, this is really where you want to get into, like this level of docs. So if you go into edge filters from path from expression to expression. So let's see. So to expression, this is Scala API. Yeah. So here we go. I think this is how I cooked up stuff, right? So it says here, oh, it's so small. Yeah. So like if you don't have someone to ask, this is kind of what I would just get into. So yeah, it is only focusing on where you end in. Okay, so let's close these guys and get into connected components. So we want to compute the connected component membership of each vertex and return a graph with each vertex assigned to a component, right? So we give some arbitrary but distinct, so this will be some vertex ID A, B, C, D, E, F, blah, blah. It doesn't have to someone order. And I want to assign, and if there's a whole bunch of stuff, so I want to assign every vertex to this component ID, right? So this is the component ID 0, right? So all of them are in the same component. That's kind of how you represent it. Okay, that's the output you want. And all these guys will be in a different component, right? So all these nodes will have, say, component ID 1, these will have component ID 2, and so on. That's what we want out. This connected components algorithm. So it's not just counting the number of connected components. So I think this is like usually, so a connected component or just component of an undirected graph, right? So this means you really don't have a notion of directionality. So what I think DataFrame does is if it's a directed edge, it'll automatically turn into a undirected edge when you ask for connected components. I mean, it'll assume that the relationship is bidirectional. So a connected component of an undirected graph is a subgraph in which any two vertices are connected to each other by paths. So it's quite obvious what it is. And So the algorithm basically, it's a straightforward to compute the connected components in linear time with the number of vertices in terms and the edges of the graph using either breadth first search or depth first search. So depth first search is another one where you start with the vertex and just keep going and then come back and keep going until you exhaust the depth. But this is what we looked at, so I think this is what's implemented in Spark. So you basically start from a place, keep going until you mark everything to be in that component, and then you make sure that you stop from every node. So it's just a slight flagging trick on top of a breadth first expansion. So then here is the, I don't know, there's some, let's kind of open this in case we have to dive into these things. Ooh, right. Oh yeah, this is important. So you know this guy, Jacek Loskovsky. I don't know, this may be busted because he keeps throwing. I mean, he's like an ungodly human. I mean, it's just really, he's a Pole. I mean, everyone knows about him. I would like to invite him one day, you know, somewhere, or meet him. So he writes these Apache Spark books. Okay, it's incredibly detailed, like Git books, and so you know, it really keeps up with the current version, and it's thousands of pages, right? I mean, I have a hard copy of one of Spark 2.2 to make sure I can dive into this if I need to. It's very, very detailed, and even Mate, you know, all the Spark guys and Databricks guys, they all sort of, it's pretty amazing. So anyway, let's hold this pointer to checkpointing. Yeah, this is just the programming guide. So what I'm saying here is with DataFrame 0.3 and later releases, the default connected components algorithm requires a setting of a Spark checkpoint directory. Users can revert to the old algorithm using .set algorithm graphics. Okay, what is checkpointing? It's to essentially so you know, you write some point of your state of computations to a directory in this fault tolerant way, but it's mainly to keep the RDD lineage DAGs from growing out of control. So this happens a lot in Prego programs and graph frames. So do you remember the RDD lineage graphs? This is the big magic of Spark, right? Yeah, so what is the RDD lineage graph?
Yeah, if any node fails, so you can track what operations or transformations you have performed, so you can get the resultant RDD which you have currently.
Yeah, so it's the recipe for that. Yeah, that's kind of the main idea, right? But the problem is, you know, these lineage graphs can just grow out of control when you're sort of, you know, doing, you know, breadth first expansion things. So often you may reach a point and it'll be good to checkpoint that. And then continue from there. So that way you're kind of culling this lineage graphs from going out of control and then continuing with your computations from the checkpointed state. So you can read about this here in more detail if you want, but from some you know, very code point of view, this line is very important. So we do Spark context.set checkpoint directory to some arbitrary directory. So this is underscore checkpoint. I'm just putting it in my DBFS.
Can you view that as some sort of intermediary cache point?
Yeah, I think so. Yeah, you can view it. That's at least the terminology is like that. Yeah, yeah, exactly. Yeah. Well, let's see. So we should. Yeah, let's just spend like 30 seconds. So it's the process of truncating RDD lineage graph and saving it to a reliable distributed HDFS or local file system. Right? There are two types of checkpointing: reliable in Spark Core and local in Spark Streaming or GraphX. So we're doing, okay, RDD checkpoint truncates RDD lineage graph. So yeah, I have to really descend into what these differences are. Yeah. Yeah, I mean, I just put my like math hat now and say I will always work with engineers who know much more Java and Scala than me, and I'm not, you know, but you have to do this, right? Because it makes sense. It's just these lineages can grow if you don't actually, you know, cache them somewhere, basically. And in fact, the Mastering Apache Spark book I showed you guys, the black book, that has all these GDelt ingestion stuff. I told you, the way we're doing Spark is very, very like kind of baby-ish, like easy, which is fine. Conceptually, it's really convenient. But to do it properly, remember, even to ingest the GDelt streams properly in a robust way, because there are these huge zip files every 15 minutes of the entire global news. We can just wget it, like I showed you in a hurry once. But the real way to do it is using Apache Nifi, which is this other robust way of ingestion. And so those guys really will tell you, when you've done a lot of hard work, compute some huge number of transformations and done some action you're interested in, you will want to cache that RDD in disk, so that when you continue later on, you don't go back and redo all of this work. So that's another thing where you would naturally cache at storage level disk specific. But this one, creates intermediate lineage graphs that are too big, so it has to automatically be allowed to checkpoint. That's what this is. Okay, so now I just do this. It's just as trivial as that. And it's a g.connected-components run. Okay, so then you kind of can view these results. Of course, it's the baby graph. It takes a long time because of all the overhead. But like my sort of, several million node graphs take, I don't know, 45 seconds. It depends on the cluster and stuff, and also the first time this was a bunch of setup. So while that's running, let's look at strongly connected components. So this is a notion we need, a mathematical notion we need, when each vertex, so when the graph is a directed graph, okay, with the edges, it's an ordered pair. So once again, it's the same. It's going to compute for each vertex some strongly connected component label that vertex belongs to. Okay, so what is the idea? So in the theory of directed graphs, a graph is said to be strongly connected or disconnected if every vertex is reachable from every other vertex, right? So reachable means you start from there and you can reach it, right? So then the strongly connected components of an arbitrary directed graph form a partition into subgraphs that are themselves strongly connected. So this is kind of notion now. So this is a strongly connected component because you can reach A from both E and from B via E, and you can reach B from A and via E, right? And you can reach E from B or from A via B, right? So that's, you see, it's a little different, right? Because there can be edges that go, directional edges that go between strongly connected components. Yeah. Yeah, so this is kind of when I get excited. So when you start like studying graphs that are, the high finest resolution, but you maybe only look at them in some coarser representations. So I told you earlier, there is these notions of, up to some regularity conditions, a lot of the definitions of Markov chains won't really work without some regularity. But up to that, what is now really neat about features like this is, so this is a little graph idea for Monday, Tuesday that John and I are trying to work on. But I'll tell you that, right? So, and it connects directly to the talk that what's his name, Michael Jordan gave from Stanford. Remember the data science revolution talk, where he was talking about privacy? So I'll tell you very briefly. And of course, these strongly connected components are the first step you would do before you get into lump Markov chain. So basically, what's going on is you have some very fine state space. Let's make this concrete. So let's say we have Manhattan, right, in this front tower. So you have very, very fine resolution, and this is an open data city, so there's so much streaming at you constantly. Let's say we're after, I don't know, we have, say, GPS locations of individuals, not just up to mass tower, but exact location, right? And then there's something I'll at least walk you through called map matching, where you will take, say there's a, this ID, some cell phone is moving like this at some rate, right? So you'll have a timestamp, you have X coordinate, Y coordinate, minimally, and then ID, right? So this is basically the structure of this. And then there'll be like another ID, which could be a taxi, and that's going a lot faster, for example. So so now let's say this is my and I ingest OpenStreetMap, right? So now what is OpenStreetMap? So let's use a different color. So the OpenStreetMap will just have tiny little dots, depending on how crooked this line is. For Manhattan, it will probably be just like this. It's pretty straight. So let's say we further up there, there's a curvy road, then of course the polyline will be a lot more. So this is essentially the nodes, and each node in OpenStreetMap itself will have a node ID. Okay. And then there will be the ways. So the sequence of nodes will form a way, like Marina explained yesterday. So a way is a generalization of a footpath or a bicycle path or a highway, right? All that extra meta information will be in columns that you will ingest using a standard OSM reader, like it works. Then that's like your finest freely available, right? In the intelligence community, they call this open source intelligence. It's completely freely available information, right? So now that's there. And now let's really go back to our social media talk. So why are we putting all this stuff together, right? Because we want this cross-domain data fusion. So that's this Microsoft terminology, Microsoft Research, right, for actionable intelligence. But then we want to add in this sort of GDPR and privacy on top of this, right? So we're now immediately getting into very challenging pure math problems. So I'll tell you exactly how. So we have social media data, right? So this is OpenStreetMap, which essentially gives rise to a Markov chain, right? It will be a discrete state Markov chain because at the end of the day, it's just people are moving between nodes, or what we can do is we can augment these nodes. So if they're far away, so in these other notebooks that Willem is trying to hook up, we can add an extra state every so many meters, depending on whether you're interested in pedestrians or cars. So these green dots and these stars will become the states of this Markov chain, like lily pads that frogs and taxis jump on, right? So of course, this Markov chain, so it's called discrete space, but then this Markov chain is also in continuous time, right? Because if your cell resolution is in timestamp in milliseconds, then it's actually continuous time, basically. So that's happening. So now on top of this, we have social media. Let's just restrict ourselves to Twitter, right? So now it depends on the city and the language and culture, but a large fraction of tweets are geolocated. So the lat long of where they're tweeting from as they're tweeting. So you have that as well coming. And remember the Z-delt streams, right? So every 15 minutes, you know exactly what the world is blabbering in, not just printed news, but also in radio and television, all like done in this big Google Jigsaw project that's sitting on these atomic clocks, and Google said anyone can download, again, completely open. So that's happening. And the what do you call it? So you know, oh yeah, GKG. So remember the example I showed you in this sort of latest GitHub from GitHub project is the global knowledge graph. Global knowledge graph is Google's state-of-the-art entity extractions done at scale of everything that's coming out of the GitHub project. So they will extract like names of people, organizations. This is a protest, you know, that spinning globe in the advertisement for this course. You know, the number of deaths and number of protests that are just directly out of GKG feeds. So that means you can find out in real time how many protests are happening here and there, blah, blah, blah. And then, of course, remember in Twitter, you also have this URL tag that Mariama, for example, went and grabbed. That's like open source intelligence across multiple domains. Now, anyone can do quite a lot with it, but say you want to do things legally, then it's interesting, right? So one of the main things I'm kind of trying to sort of, you know, say is an interesting math problem is, for example, if I restrict myself to not being able to identify a specific individual beyond a certain threshold knob of privacy, say at any given time I should not be able to know more than K individuals at a certain time. And unfortunately Amelia isn't here, so she kind of talked about this a little bit with me, this notion of K privacy or something. So how do you guarantee that your decision procedures, your mathematical models, your inference tools are going to guarantee this minimum bound of K, right? Now that becomes of interest to law, right? So I can actually say you as an operator that's working on AWS cluster on Swedish soil has to conform to Swedish sovereign law embedded within EU. That's specifiable in one of those things from 1998 law. So it's there. So then, because you know we're trying to write a VR grant, right? It was Swedish twist, but it's a good law, right? And in fact, Duma did the same thing. So Russia, for example, kicked out LinkedIn about months ago because they didn't conform. They're given a whole year to move all their LinkedIn Russian citizens' data to Russian servers on Russian soil, and they didn't, so they were kicked out. And anyway, now they're in a hurry, I think. So then, what I'm saying is that we need to have a many-to-one mapping. Many-to-one mapping from the state space here, right? So many of these states, one possibility is a lot of these states could get lumped to the same state. Okay? So this is kind of a lumped. So let's put a yellow one, right? So this is like a lump. So when any kind of activity is happening here, I only know it up to this, right? So if a person stays there for like a long time, I'll only know that they were in this little lump state. So you can do this at the whole resolution of OpenStreetMap. Okay? You can do the lumping in the ideological spaces as well, right? So you can sort of not really identify people beyond certain clades of some retweet forests or whatever, right? So these will be able to, because we hold everything tight, we can kind of guarantee that we will not release the ID, Twitter ID of the individual if that Twitter ID of the individual falls, within a clade that has at least so many leaves or whatever. So, I mean, I'm slightly blabbering, but at least that's the idea, okay? Because now we can start doing some really hardcore math stats like Jordan was talking about, right? He had the privacy knob, he was talking about local privacy, but still the estimators, the statistical procedures have to have proper statistical properties. So we can start thinking about these things in these spaces, which are, as far as I know, like open problems. Okay, so that's kind of maybe too much of a motivation for strongly connected components, but strongly connected components are extremely important because they are the generic topology of the Markov chain, because ultimately a Markov chain has to have directed edges. We cannot say, because you can't even in road, cannot go the other way, right? It's one-way traffic or whatever. Okay, so let's do this. And again, we'll just kind of So this is a depth first search linear time algorithm. So we can get into this in more detail. I think, yeah, so do you guys know Donald Knuth? Well, of course. Yeah, do you know? Oh man, he's the man. He's alive still. So I learned a lot of stuff I know from Knuth's books. Like I actually finally got them autographed. He brought us LaTeX, right? He brought us Metafont, and he's this professor of art of computer programming. That's his famous book. He sat down and wrote the entire Metafont by hand on pencil paper and then coded it. Right? He's very unique. He's also very religious, and he actually celebrated his 70th birthday? Yeah, in 80th. Oh, yeah, it's Knuth 80. Yeah, his 80th birthday in PTO. And because PTO has this amazing organ that mixes 1/3 of it is French, 1/3 is German, and the other third he says is the future organ. So I don't know if you know, PTO has one of the best organs in the world. So anyway, this is Donald Knuth, and his books are what I would recommend, like if you want to actually, if you want to really get into maths and whatever, thinking, programming. This is a series. It's a great gift. Yeah, I just have the first 3 volumes. So why did I mention? Oh yeah, I mentioned Knuth because he told me in PTO that he actually answered a question at the big seminar that was there for him. Do you remember? Someone asked, "What's your favorite algorithm?" And then he said, I don't have favorite algorithms, but if I have to say one, then it's this algorithm by Bob Trajan strongly connected components algorithm. So this is Knuth's favorite algorithm. Right now, Bob Tarjan is working on some amazing stuff. He showed me in PTO on zip trees, but I haven't read his preprint yet. So anyway, these guys are, and in fact, Uppsala math department is quite heavy duty on randomized algorithms. So we have some very clever people here in this world. Okay, so that ran, and what we are getting is that this is the component ID. It's kind of a long, it's somehow chosen. So we know that these guys, Alice, David, and Esther are on this, and this guy too. Fanny, Alice, David, and Esther are on the same strongly connected component. Gabby looks lonely. Gabby is by herself. So, and then Charlie and Bob are, yeah, we know they could reach each other anyway. Okay, and then if you compare this with the output of the previous run, you see this is just the connected components, right, which treats it as an undirected graph. Everyone is in the same connected component except Gabby. Anyway, so Markov chains will really be working on this level and some regularizations. Regularizations here just mean like with some probability you'll make them kind of hop around a little to make the maths easy. But
I didn't get the same result.
Oh really? Oh, the numbers, integers may be different. Is that what?
But Fanny was not in the same component.
For the strongly connected component, or this one? Really? Strongly. Okay, this I'm going back to the connected components algorithm.
Yeah. And when I run the same thing here, and Fanny is on a separate component.
Oh, really?
Yeah.
That is crazy. No, that's okay. Well, we just visualized this graph, right? Let's just... Huh. Really? Okay, that's not good. That's a subgraph. Okay, let's look at this. Where is the name? So because these visualizations are undirected, right? Oh, where are we? Oh yeah, here we are. Oh. Yeah, so actually I don't know what I'm feeding the algorithm. I don't know what I made G to be. Okay, let's just visualize G once more for me. Because because I have no idea. So can you guys like copy paste that cell and visualize the G you pumped in and see if it makes sense? Because it has to, otherwise like something is not at all good. Oh, that's what I thought I was explaining. All right, just give me a sec. I just want to just so what's my G here?
Sorry, it's probably my wrong. I was probably ahead of I was looking at strongest and negative graph, not that one.
Yeah, so okay, so I have this, and I have A, B, C, D, E, F, G, and I won't be able to see the one that's not there, G. Yeah, this is kind of sad because I'm only visualizing edges that are there, so if it's a single node, I don't see it. Okay, I'm happy with what's happening under my hood. Yeah, I mean, I think we better kind of move on because I really want to finish graph frames. I think you should look at the Wikipedia page because I kind of already like, yeah, you know, just should make sense because what is this? Oh yeah, it's the same G, right? Yeah. So. Yeah, I mean, this is not the best visualization because you really need to put a directed arrow to... Is it trivial to put a directed arrow on D3? No, it's not. There you go. Okay.
Now with the first graph.
Right. That's a bummer. Anyway. Okay, label propagation. So this is, I think, one of our main community detection algorithms. So what's the idea? So, so of course this is static label propagation because the graph is not changing right now as we're doing it. Each node in the network is initially assigned to its own community by a label, okay? And then at every super step, this is this Pregel language, all the nodes, each node sends its community affiliation to all its neighbors. It says, hey, I'm a whatever, I'm from PTO, whatever, you know, some community, some label. Let's say I'm integer 84 and you're 78, and so I tell all my out neighbors I'm 84, and you tell all your out neighbors what your label is, you know. And then in the next step, you basically the update step is the neighbors receive all of their incoming messages and they simply take the median of these labels. So it's this sort of median propagation. Okay. To the mode of the community labels. So then that's sort of, you can imagine that'll stabilize at some point. It's heuristic. So then, you know, it's heuristic because you cannot guarantee that this algorithm will converge. And one can also end up with very trivial solutions, like all nodes are identified into a single community, although there may be some community structure, but these are. But it's super cheap. It can easily work because it's in this Pregel model. And I would sort of recommend getting into that because this whole class of label propagation algorithms are very rich. You don't have to just do mode, you know, you don't have to update your state by the mode of all the community labels you receive. You could do other things. Okay, so that's just a Wikipedia link on label propagation. So here, let's look at this. I just run this label propagation, and I'm doing only 5 iterations. So the number of iterations is also a nice way to kind of see how the mode propagates. Okay, so for example, if you had Trump, and I've done this with Trump stuff and Hillary, you know, whatever label is initially assigned to, so everyone initially gets their own labels, unique labels assigned. And because Trump has so many followers in my design, and so does Hillary, they will immediately get absorbed by one of the labels in their community, you know, because the node will really quickly propagate into that community. So eventually they'll all get the same label, all of Trump's followers, with a very high probability. Okay, so that's what this is doing, and you can just display the results, and now you can see these labels are the community labels, right? Which is not the same as a connected components. It's a bit more leaky. So the idea is that it's going to capture highly connected, you know, communities are kind of loosely defined as subsets of nodes that have a lot more connections amongst each other than between them and outside. It's kind of a, okay. So let's get into PageRank. So PageRank, again, I blabbered about it a lot, and this is basically here. So you see, this is a web page. It's fat because if a frog kept on jumping, you know, with probability 0.85 from wherever it is to one of the two places it could go to, or one of the how many ever places it could go to, with probability 0.85, and then choose one of the lily pads at random, like the probability 0.15. In the long run, this is the relative frequency of visits to each state. That's basically PageRank. Yeah, it's a stationary distribution of a Markov chain, yeah. But you see, what they did was, that was clever, is that, you know, this is a directed graph, and they don't have to worry about what's the number of strongly connected components and all this. They don't have to get worried about getting trapped into some little place, and because they did this 0.15 probability of jumping from anywhere to anywhere. So it's kind of made the math like boom, which is fine. It's just ranking web pages. So anyway, I think this again is a, yeah, so I mean the pseudocode is in the GraphX paper. You should really read it there before you descend into details on this. So this is essentially my reset probability. This is the sort of jumping to anywhere, probably 0.15. Tol 0.01 is the tolerance. That is, when do I stop? So when my nodes, the state that they're updating is this stationary distribution, right? If that doesn't change by more than 0.01, I terminate the algorithm. So now we have a purely what is called a vertex program. In fact, it's a distributed vertex program that's fully scalable, that is simply computing the stationary probability of an irreducible Markov chain. That's pretty cool. Yeah. And the really cool thing is you don't have to put all the edges from everywhere to everywhere, right? Because that's taken care of in the message passing interface. Yeah? Yeah. Of course, the stationary distribution is conditional on the transition probability structure. So the default one in the original paper is 0.15 of going anywhere. But you can change this, and you know, let's change this. Okay, if you can remember these numbers. So now I'm just a bit more crazy frog. Like the higher probability, I jump everywhere. So this will change. I don't know. I forgot the other numbers. Yeah. Anyway, you can also control by number of iterations and things like this. Then you'll start seeing how, you know, where you kind of reach infinitely many steps. And there's lots of bells and whistles. There are a whole lot of hundreds of papers around this. There's something called personalized PageRank, where, you know, let's not go there. They're all Pregel programs. So here is just the showing the edges now. So now I have this new thing called weights, and so that gives me this is actually just the edge probability. Yeah. So then run PageRank for fixed number of iterations. This is the other one I said. So these are good things to play with. So if you say do your own Twitter experiment, get a little retweet network of say a few hundred thousand, say 100,000 whatever accounts of interest to you, then you can essentially turn that into you can leave it as it is. You can leave every retweet as its own link. You don't have to really add weights necessarily, and simply run this and see what happens. Run the PageRank. It'll kind of tell you, it depends on how you encode the link. So if the retweet is, if say A retweets B, then, so I usually go from the original tweeter to the retweeter because I want to track the flow of information. But I think if you encode it the other way, the PageRank will make sense because it's anyway, it's up to directionality. So you should be able to find the most influential original tweeters of the most number of retweets in your Twitter collection just by some playing around. And then this is what I was saying as personalized PageRank. So you basically start from a source ID and you just see how things happen from there. And so it'd be like Spotify. Any kind of basic recommender system is twists on this, right? So I want to know, like, well, it's a bit more than this, but it's a similar idea, right? So you will, maybe you'll do some breadth first expansions up to say some level, and you'll have some motif finding on find me all the people that listen to this genre and that genre of music, and then you just bottle up like a bunch of other things they listen to that this guy doesn't listen to. It's basically recommender systems, and it's a mix of this kind of personalized page ranks. And so a lot of these papers are out there, and just search in Wikipedia. But I'm just giving you the primitives. So here is shortest paths. So this computes the shortest paths to the given set of landmark vertices, where landmarks are specified by vertex ID. So in my Twitter example, these are the influential nodes of interest or whatever, right? So they're called landmarks in the original algorithm. So let's just quickly run through this. All I have to do is do shortest paths, and then I have to give this landmarks method, and to it I have to give a sequence of the specific landmarks I want to start from, right? So and it will return to you the usual vertex information, and then it gives you these distances. Okay? So it says the distance from A to A is 0, the distance from A to D, the shortest distance from A to D is 2, and so on. And this is exactly what I did in my talk, right? I did a little bit more work, weights and stuff, but essentially when I took my retweet network and then I took the edge weights and I did 1 divided by 1 plus the number of retweets, I had this nice probabilistic interpretation. Then I just pumped that into the shortest paths algorithm. And then I had Trump, Hillary, a bunch of other American politicians, and then in 7 different hate groups, I had 13 different landmarks. And so for every vertex, every Twitter user, a few million in my collection, I got this big list of shortest distances to all 13 landmarks. And because I ordered my landmarks it was an ordered list of 13, I can embed that in Euclidean coordinates, and I just did Manhattan distances, to find the distances. For every pair of users, I can look at these 13 integers and another 13 integers and find the absolute difference between them. It's called the Manhattan distance or the L1 distance. And that's all I used for pairwise distance. And then I use that pairwise distance to build these forests, right? Because that's an old algorithm from the 70s called the neighbor joining algorithm. Anyway, this is triangle count. It's basically the same. This is also a Pregel program, so you can peel all of this under the hood and see how simple the message passing layer is, the initialization layer is, the update layer. There's only 3 components to it. Yeah, so here's the assignment while that's running. Yeah, let's open this. So I guess, if you're consulting and, and your boss says, oh, I'm going to give you a performance-based bonus, then you probably want to get into this, right? I mean, you know, a little bit. I mean, I'm not saying invent your own algorithms, but you may want to descend into this very simple aggregate messages library and use the Pregel API. Now you can do quite a lot. So you can decide, you know, you basically have to send to source and then send to destination, and then you have to have some way of aggregating or updating your state. That's basically it, okay? So all these things we've seen are in this class, in this Pregel class. Because everything in distributed vertex program you can do with Pregel programs. But so assignment, apply one of the Pregel programs such as community detection or whatever for finding the number of triangles or connected components on a data set you have found or ideally collected using your Twitter credentials from last week. Oh, that's a good assignment. What do you think? No? Well, I don't know. I made it long ago. I don't remember making it last night. For example, build a retweet network of directed edges and find the number of connected components. You know, it's not, because you're going to do that other one. If you do that other one, if you don't do the other one, then just do something else. I don't know. And I honestly think, you know, it'll be a very good idea to do this homework in a way that's good for you, you know, which is I don't remember, you know, I had like some kind of advice at some point. I don't think I shared this notebook with you guys, but I think at the very bottom of this, there is some advice from sort of people in the real world, like data scientists who've changed their careers or retrained themselves. So they kind of tell you, yeah, they tell you intro to data science for academics. I have no idea what this is. So I think there is somewhere here, there is a blog. Let's find this out. I think it's this. Yeah, I don't remember. So anyway, all he says is like you basically, anyone can be a data scientist. They just have to elbow their way, and you have to show that you do data science. And the way you show that is to just have blogs that are publicly posted, so you know Google bots find you. And I don't think it's this one. I'm not sure. Yeah. Anyway, doesn't matter. So there are some people that recommend this. So that way, you know, your Databricks notebook can just be your sort of technical blog, and you can constantly improve it. You can hit publish and choose the thing that says keep publishing as I change, so it can be. And then it's easy for me to grade it too. Okay. I'm happy with what we covered. Are there any questions? Okay, so let's meet at 1:30 then.